an intro to the tooling that we have, which is GroqFlow and also MLAgility. So for the agenda we have at the beginning, we're going to go through a high-level overview of the software stack, and then we're going to talk about GroqFlow and how that abstracts away a lot of the elements of the compiler and allows you to go from a model in a high-level framework, for example, PyTorch, into an executable, which has been compiled and can run with the Groq runtime. And once we have an executable which can run, we'd like to be able to benchmark this against other platforms in the market right now. And for that, we have our own benchmarking tooling. It's completely open source. It's called MLAgility, and we'll be going into a bit of depth about that as well. All right. So let's talk about the software stack. Hatija tomorrow will be talking about the GroqWare seat in a bit more detail, but right now I'm just giving you an introduction, mainly focused on the left-hand side for AI. And let's begin over here. So the Groq LPU is designed for low latency, batch one, deterministic, scalable AI inference. And once we talk about AI, we can't kind of escape these high-level frameworks, for example, PyTorch, TensorFlow, Keras, JAX, and so on and so forth. And most machine learning engineers, myself included, we'd like to be able to go from these frameworks, writing a model in this framework, to being able to run on whatever hardware platform we may have. And that's something which we do provide with our Groq compiler. And let me just walk you through a high-level overview of how that looks right now. You go from your model from PyTorch, for example, you lower it into an Onyx graph. And on this level, I do want to make sure that, as Andrew mentioned, we work with static graphs right now. If we were to work with dynamic shapes, for example, that would almost break the determinism. So for right now, it's static graphs within the Onyx framework. We lower this down into MLIR, which is almost the de facto standard for intermediate representation right now. And that's translated into our own MLIR dialect within the compiler. We take this to the assembler, and then we get an executable and IOP, which can then run on the runtime. Philip Larson will be talking a bit more about the compiler tomorrow, and also Aviv will be talking about the runtime tomorrow as well. So rest assured, we'll be going into a bit more depth about these components. But right now, I'll be talking about this left-hand section over here. It's called GroqFlow. And what this does is it's almost a highway which abstracts away all of these components, and it gets you from PyTorch to an executable which runs on the Groq hardware. All right. And as I mentioned before, once you have something which runs on Groq hardware, we'd like to be able to benchmark this. And for this very purpose, we have our own tooling called MLAgility. It's completely open source, and it allows you to benchmark a variety of models, whatever model you may want, against multiple hardware platforms. Now, we also have this available online. Give me 1 second. It's on a Hugging Face page right here, and that's publicly available. Oh, give me 1 second. I guess that link was just out of date. All right, so we have all of these benchmarks publicly available, and we regularly update these numbers, especially when we go from SDK release to SDK release. So stay tuned. We're always adding more models, adding more benchmarks, and improving performance. But before I go on and talk about this page, I'd like to just kind of direct your attention towards this warning sign at the top. This is currently under active development. We're going to show you how you can use this code base, but please bear in mind, maybe some things won't work out of box, but for what we've tested, it does work, and we hope you play around with this. All right, so now that that's done, let's walk through this Hugging Face page. What we do is we take a variety of models, all open source, so maybe from Torch Hub, Torch Vision, Hugging Face, and you can add as many models you want on here, by the way. We have our own internal system, and we have around 1,000 models running right now. And we take it through the entire workflow that you've seen before into compiling and also running it on the Groq system. So you can see, let me just kind of change it back to how things were in March of this year. We tested on the same number of models, and we could run 31% on the Groq system. And the performance we got against, let me benchmark this against the A100, on average, we get a median performance of 2.63 above the NVIDIA offering. And like Andrew mentioned before, we're always continually improving the performance of the compiler. And this was over the course of 7 months, and we've improved fairly significantly. And we will continue to do so with each SDK release. Let's just go a bit further down. We can see the platforms we're benchmarking against. I can talk more about the runtimes and also the methodology a bit later on. But for now, we're using GroqFlow for the Groq chip. And also we're using TensorRT for the NVIDIA platform. And over here, you can see the origin of these models. A lot of them are from Torch Vision, also, these public repos, and also Hugging Face. And over here, you can see almost a CSV detailing all the performance for all the benchmarks we have. And later on, I'll show you how you can generate the CSV and how you can even create this web page on your local browser. But before we go there, I'd like to talk about MLAgility and the rationale for having it in the first place. That's kind of one of the topics we have over here. Why do we have MLAgility when we have already so many benchmarking strategies out there? And let's focus on MLPerf. MLPerf has a handful of models. And what this allows you to do, what it allows vendors to do, is actually write handwritten kernels to be able to optimize for whatever it is in MLPerf. So what that means is you may have amazing performance within the MLPerf suite, but it doesn't necessarily generalize to models outside of that. And thinking about how the landscape's changed in the past few months, we're probably not going to have enough animals to name our LLMs, and maybe next year. The landscape is continually changing, and we do need a framework which allows you to benchmark whatever hardware, whatever software stack you have with the hardware on all the models you have out there, which gives you more of an idea of how the software stack and also the hardware stack could do for your model as well. All right, so let's go back to the presentation. We talked a bit about MLAgility. Here is a high-level overview of MLAgility. As you can see on the left-hand side, we take models from open source repositories. You can add your own as well. We've had a few researchers from Argonne, and we wrote a paper benchmarking micro benchmarks for graph neural networks, and that's something we published earlier this year at ISC. So you can use whatever model, whatever micro benchmark you may want, and you can benchmark this on whatever hardware platform you may want as well. Right now we have the NVIDIA offering, Groq, of course, and also Intel x86, but you can add your own, and you can see how each do against each other. Let me just move this aside. And like I mentioned before, for the Groq system, we're using GroqFlow. For NVIDIA, we're using TensorRT, and we're also using Onyx Runtime CPU for the CPU. All right. Let's move to the next slide. All right, so to kind of recap that introduction, we port models with GroqFlow and we benchmark them with MLAgility. It's really not that much going on. And for the next few sections, we'll be going into how you can port your own models with GroqFlow and how you can benchmark a suite of models with MLAgility.